a look at the stack. Sorry, I don't know how well you are able to see that. So I'm at the end of the main function when everything that are local variables are distracted. So in particular, the vector of threads gets distracted, which means each of the threads gets distracted. So here are some functions. So it's the distractor of the vector, and see it's the distractor of the vector. It calls some functions. Eventually, it distracts each of the elements. So we have the where is it? Here it is, the distractor of the thread. And if the thread, it even calls this joinable function. So if the thread hasn't been joined, it throws an exception. Again, why doing that? Why requiring to properly call join before distracting the thread variable?
Because we don't want to terminate threads randomly. We want them to close properly.
Exactly. So it's exactly the same reason. When the main function finishes, it will terminate all the threads, and we don't want them to be terminated. Now, of course, the library doesn't know, the framework doesn't know when will this happen. So there is a check that is done on the distractor of the thread variable. And if it finds that the join hasn't been called on that thread, then it will signal this.
I think we can also detach the thread and let it continue separate of the program.
Yes, that's also a possibility. I haven't seen programs where this is done, but it's possible to be done, and then you have to somehow make sure that the detached thread is either terminated or it's not left in a bad state when the program terminates. Anyway, as far as I know, it's when the main function finishes that the whole process finishes. So you don't leave only the background threads. But indeed, it's possible to detach a thread, and then you don't have to, actually, you cannot join a detached thread anymore. But it's harder to make sure that it doesn't do things you don't want to do. Okay, so those are the threads. Now, creating a thread takes quite a long time. It's an expensive operating system function, probably on the order of magnitude of some thousands or even tens of thousands of simple instructions. There's a lot of work to be done for a thread because there's a stack to be allocated, there are registers to be initialized, there are lots of operating system data structures to be filled in for keeping track of the thread. So it's an expensive operation. Another thing that is expensive is doing a context switch, changing the current thread that CPU is executing. So thread, you can consider, if you are writing a program, you look at a thread as something that executes instructions. If you look from the operating system perspective, a thread is an object represented by some data structures. from the operating system perspective, you have the CPU cores that are actively doing something. And a CPU core may execute instructions for one thread or for another thread. And you will switch between eligible threads. You will have threads that can be scheduled and threads that are waiting for some external conditions. And if a thread can be scheduled and you have a CPU that doesn't have anything else to do, it can start or resume executing that thread. So it jumps at different moment, it jumps from one thread to another. But jumping from one thread to another is also an expensive operation because it means saving somewhere all the registers that hold data pertaining to the current thread. So instruction pointer, stack pointer, all the other registers. Load them for the other thread and jumping to the current instruction in the current thread. This means invalidating a lot of cache. So that thread was using some data that is in the cache, and now we are jumping to another thread that possibly has no data in the cache, so we have a lot of cache misses. And again, it's maybe some hundreds or thousands of instructions worth of penalty when switching the context. So if you have, let's say, a single CPU and you have multiple threads, you have to have in mind that they cannot execute at the same time because you have a single CPU. And whenever the CPU switches from one thread to another, it pays a penalty. Now, if you have multiple CPUs, it's possible that you have one CPU for each thread and they effectively execute in parallel. But again, if you have more threads than CPUs, you will have lots of context switches. And spoiler alert, we will have to create threads for taking advantage of the multiple CPUs. But if we create too few threads, in an extreme case, we keep all the computations on the main thread, we don't take advantage of the CPU cores. If we have a single thread and 8 CPU cores, then one CPU core will execute that one thread and the other 7 CPU cores will do nothing, will waste time. On the other hand, if we create 1,000 threads, so more threads than CPUs, then only 8 threads will be executed at any given time, and we will have lots of context switches with CPUs jumping from one thread to another to cover all the 1,000 threads so that all of them progress somehow. So we are in the situation like this. Now imagine those are threads, and this is what a CPU core is doing. So executing something from one thread, then going and executing something from another thread, and so on. If we have multiple CPUs, then it's possible that another CPU takes here a part of this thread and executes a part of it. And you should realize by now that it's there are a lot of things to be taken into account when designing and implementing the operating system to optimize this task switch process. If you have a CPU that is free here, it can execute some instructions from this thread, but it's preferable to have the same CPU continuing this thread because of the caches. Because the first CPU probably has something in the cache regarding to this thread, and if you switch to another thread, to another CPU, then the new CPU will not have that data. So there are lots of details of optimization, but from the perspective of the programmer, it's easy. Each thread executes instructions more or less in parallel. Now, a problem, well, we have to somehow synchronize what the threads are doing so that, first of all, then they don't destructively interfere with each other. They don't step on each other's toes. And that's the mutual exclusion problem that we started discussing and that you have in the first lab. And so this is one of the basic problem of the two basic problems that we have to solve. The other basic problem that we have to solve is I guess it's here somewhere, regarding the condition variables, is that one thread computes something and then one or more threads need that result in order to continue their execution. And that's the producer-consumer problem. So those are the basic things that, let me put a note to having it in mind. So those are the two problems to be solved. So mutual exclusion in various forms and producer-consumer. So mutual exclusion is we have two threads that operate on the same data, and we want them to not distract each other's work. And producer-consumer means we have one thread that produces some data and one or more threads that need that data. And we have to somehow pass the data from one thread to another and make sure that the consumer doesn't start using the data that has not been initialized properly. Okay, so we'll talk a lot about mutual exclusion. And we have by the way, here is another example of a mutual exclusion problem. If you get the joke, the punchline of the joke. And the idea here is that each thread prints some of the words of the phrase. But if they get in the wrong order, then the phrase isn't correct. If you rearrange a little bit the words, you get something that's meaningful. By the way, you can encounter a problem exactly like here if you have multiple threads that log some messages in a log of the program or print something at the console. And typically you want each thread to print or complete lines. You don't want to have a line with words from multiple threads. Now, to solve this problem, there are two kinds of solutions. One is to have atomic operations. The second one is to have mutexes. So let me put it here. We have atomic operations, atomic variables. And the second is mutexes. Now, let's start with atomic operations. They are implemented by using some hardware support. You cannot do it otherwise. So essentially, there are processor instructions that do a bit more than simply doing the arithmetic operation on a variable. They also protect if you have this picture with the cache. If I execute an operation here, a simple operation, it goes into the cache and performs the operation without caring too much about what can be here. If you do an atomic operation, it won't execute until it makes sure that the value of that location is properly synchronized between the caches. Now, it's a bit recent that those atomic operations are standardized in a programming language. So, for instance, in C++, it has been done around 10 years ago, and some issues have been discovered since and fixed. And up to then, you didn't have a standardized way of doing the things. In C++, you include a header named atomic. You have a template. So I can declare a variable as being atomic. And then we have some basic operations on it. So for instance, this program, let me make sure, yes, it's the correct one. We create a number of threads. Originally, I put 16 threads. Let me go back to 16 threads. So the main function creates 16 threads. Each of them executes this function, and then it ends. Then it waits for the threads to finish, and it ends. And each thread performs 1 million operations, each operation being incrementing the variable. Now, if I use a regular variable and I execute the program, by the way, it's in release mode on 64 bits. It's very quick, so it prints here 1 millisecond. It's probably around 1 millisecond. We can put it better. Microseconds. Like this. Okay, now it took a bit more. Now it's 2 milliseconds. But we notice that we don't have the correct result. So we have 1 million increments for each thread, and we have 16 threads. And the result that we are obtaining here is 7 million instead of 16 million. Now, it's a bit interesting that we have such a round number, but anyway, it's wrong. So we have to tell that we have an atomic variable for the sum. Now the execution takes quite a bit longer, so it's 141 milliseconds, but the result is now the correct one, it's 16 million. Why does it take quite a bit longer? Because now the compiler knows that this is not a regular integer, but it's an atomic integer. So this plus equals operation is something a bit more complex that so the machine instruction that is generated behind locks the variable, so tells the other caches, please don't use this memory location, and this takes quite a longer time in order to get the correct result. Now, the atomic operations are easy to use for simple operations. So if I have to add a number, be it constant or not, it's quite easy. Let's see a little bit what operations do we have. Std atomic. And here it is the list of types for which we have this. Now it's a template and it can work for quite a number of data types. I guess it's something related to the size and whatever we can do. But essentially, we have the operations that are here. So we have the plus plus and plus equals operators, plus equals, minus minus, and minus equals, logical, bitwise logical and bitwise logical or bitwise logical exclusive or. Those are the allowed operations because those are the operations that typically have support from the operating system, from the microprocessor. We cannot do other operations. For instance, we cannot atomically multiply the value with something and atomically write the result of that operation. So the set of operations is quite limited. And going outside this limited set of operations is a completely different story, and it's much harder to do. But before going there, you can notice that even those operations have something a bit more. We have the operators, for instance, like I used here. So here I put plus equals 1, but I can write in a different way. I can say sum fetch add of 1. It's exactly the same semantic. It's exactly plus equals 1. And you can see for each of the operations here, I have the operator and I have a named function for the same purpose. I have fetch add, fetch sub for minus, fetch add, fetch or, fetch store for the logical and or and exclusive or. Now, if I look at the operation here, I have two more things. The first thing is that it returns a value. And if I look in the documentation, I find that it returns the value that was before executing the operation. So I have, if I get the return value from here, I get the value before the increment. And that starts being interesting because you probably used something called Std Shared Pointer of some type. Do you recall what a shared pointer is?
It's a smart pointer which keeps track of how many references there are to that pointer and allocates the memory address when there are no more references, and it can be accessed by it can have more than one reference, so even across multiple threads, I think.
Yes, very good, even across multiple threads. So I have a variable sitting on a heap, on the heap, and it's pointed from a pointer here. And if I copy the pointer to another variable, I have to keep track of how many copies do I have and when should I delete the heap allocated data. If I delete it too early, I get dangling pointers. If I don't delete it in time, I get a memory leak. It stays there allocated. I cannot use the memory. Moreover, the destructor may free some other resources. For instance, it's very common that a destructor closes connections, files, and so on. And that's even more problematic than simply the memory. With the memory, we have languages that have a garbage collector, like Java, C#. And in those languages, I can afford not to care much about deallocating the memory, but I still have to close the files and connections in time. And it's even harder because that means I have to keep track of the references for only those variables. Anyway, the shared pointer works like this. In order not to force this data to be constructed in another way, let me use a different color. I'll put this orange. It keeps two pointers. So a shared pointer is actually a pair of pointers. One pointer points to the object itself, and the second pointer points to this counter. And here I have the number of variables. So in this case, I have a 2 here. And here is the pointer from the second shared pointer to the reference counter. Now, if I create a new copy, then the new copy will have the object pointer pointing to the same thing as before, and the reference counter pointer pointing to the data structure here. And this means I have here now a 3. Now, the shared pointer is half-thread safe, in the sense that on one hand, I can have an assignment that creates this as a copy of this on one thread, while a second thread has this one and does whatever with it. Even it creates a fourth copy of the pointer. So from this perspective, it is thread safe. What it is not thread safe is to have two operations on the same shared pointer. So I will use this place for comments. I'll do something like this. Shared pointer of int, let's say I have something like this. What is, how to put it? So I have a something that is thread safe is to say something like this. I have a shared pointer to an integer, and I create a new thread that gets a function g and gets a copy of this shared pointer. So I will have a void g of shared pointer q, and it can do something like this. And I create a thread that operates on the object behind that shared pointer. It does something like r arrow whatever. And here I do p arrow whatever. So I can operate on the object, assuming that the object itself is thread safe. And I can create copies of a shared pointer, or I can reassign a shared pointer. I can say here p reset of new int, let's say with some value, and it is safe. It's thread safe. What I'm not allowed to do is to have a shared pointer that's shared between threads. So what I'm not allowed to do is to say here GS takes whatever value, and here GS arrow and do something with what's located there. So this I'm not allowed to do. The other one I am allowed to do. So taking copies and assigning it to a different value. But back to here, let's say after I have this picture, on 3 different threads, I destroy those 3 pointers. So each of these shared pointers is destroyed on a different thread. First of all, each destructor must decrement the counter here. And the last one, the one that decrements it to 0, must also destroy the object here. How do we achieve this? So incrementing or decrementing the shared pointer, the reference counter here, is relatively easy.
Should be done with an atomic variable.
Yes. So this is an atomic variable. And I do something like this, plus plus or minus minus. Now, to find out if I'm the last one, that's a bit trickier. But with the return value, I can do that. So it will be something like void delete reference, and I have an atomic int pointer p ref count. And what I will do here is if 1 equals pref count fetch subtract of 1, and here I go and delete the object as well. It will be something like this. So I have this operation that is atomic. I do the arithmetic operation and I get the value that was before. So if the value that was before is 1, it means that I was the only owner of the object at that time. Nobody else has any other reference. So this means nobody else could have incremented the value in the meanwhile. So now there are no references except for the current one, so it's safe to destroy the object as well. Now, this was the first issue regarding those atomic operations. The second issue, and I'll come back a bit later, is this second argument, the memory order. I'll talk about that later. As you can see, this has a default value, memory order sequential consistent, and that's the easiest to work with and the safest one, but also the most expensive. I'll come to it a bit later. Or maybe let's do it now.
I have a question though for the atomic variable. I guess that the if that you have created there isn't really perfect because we can still have another thread acquiring that shared reference, the shared vector between actually comparing and fetching the data from the atomic variable.
What do you mean?
In the delete
Here?
ref function, yeah. So we can have another thread creating a shared pointer after we fetch the data from the variable, but before we compare it with 1.
Yes, we have to have in mind this possibility. So indeed, the atomic operation is just that. The value is decremented and we get the value that was just before decrementing. Now, if the value before the decrementing was 1, it means that we are the only owner, or we were the only owner at the time this atomic operation was performed. And having there a value of 1, it means that no other thread has the value, has that shared pointer. Because it's 1, which means it's only us.
Yeah.
We are the one. And in this particular case, we know that because of the semantic of this value, no other thread can have that pointer, and so no other thread can increment it in the meanwhile. But yes, you are perfectly right. We have to have in mind this possibility that what's atomic is until this function produces a value that it returns to us. Everything else is fair game. So from the moment the value is generated until the moment we do the comparison and do something, decide what to do, anything can happen. Well, anything that can happen with that data. And we have to be mindful of what can happen and what cannot happen. And by the way, this is the reason why working with atomic variables is hard, because we only have very short atomic operations, and any succession of atomic operations is not atomic. If I put two fetch adds one after the other, it's possible that some other thread does something in between. That's why with mutex it's easier. Let me see if something isn't right. Let me comment everything and let me rebuild. Okay, do I have some warnings? Probably not. And the time used is the same. Okay, so just a preview of, I'll come back to those a bit later in order not to take now all the time. We have a second argument for fetch add, fetch sub, and those named functions. And this has to do with reordering of the instructions. So one more thing we have to have in mind is that, let me go back to okay, so let's consider a producer-consumer problem this time. And I have something like this. I have a producer thread that computes a result, performs some computation, and the final value is written in a global variable called result. And then it has a global flag that it sets on true. It's initialized with false, and we set it to true after the result has been set. The consumer thread, when it realizes that it needs the result, it has here in the simplest form a busy wait. It waits for ready to become true, and then it uses the result in some computation. It's a very classical approach. Now, it looks right at the first sight. The problem is that both the compiler and the CPU itself do some optimizations. And the result of those optimizations is that the execution here may not be correct. And here is why. I said last week that the CPU parallelizes the execution of the instructions, that it executes several instructions at the same time. Now, the several instructions must be independent of one another. If one instruction needs the result of executing another instruction, then they cannot be executed in parallel. So both the compiler and the CPU itself are allowed to reorder the instructions in order to optimize the flow of instructions. But in doing so, both the compiler and the CPU have access only to the local thread. They cannot guess what's happening on other threads. Now, let's look at this thread with the eyes of a stupid compiler that doesn't know what those variables are to be used for. So I have two assignments that are independent from each other. Here I set a value that is a constant. Here I set a value that is the result of some computation, but the variable here obviously does not is not used in the computation. So there are two completely independent assignments, and the compiler will be allowed to reorder them. To see why, imagine I do something like this. A equals some expression, let's say f of something, and b equals another expression of something else. Now, those can be parallelized, and as a programmer, I want them to be parallelized. There are two independent computations in this case, and they can be parallelized, and I don't care, and even I want them to be parallelized, and I don't want to rest on me as a programmer to optimize the flow of instructions. I want the compiler or the CPU to do that. But if the compiler cannot see the difference between this case where I don't care about the order in which the computations are done, and this case where I want that the last thing to be done is to set true to the ready variable. So the compiler may set, unless I tell it explicitly, it may move the assignment somewhere before, so before the result is ready to be taken. And here as well, it may happen that the compiler or the CPU reorders the instructions so that the test for ready is done somewhere in between doing the computation based on the result. Again, because the compiler and the CPU don't see, when looking only at a single thread, don't see any relation between those two variables. It's only us that know that such a relation exists.
I think it may also happen that it can see the ready marked as false at the beginning, and in the consumer thread in the while, just replace it with while true while optimizing, and that's also an issue that can happen.
Yes, very good remark. So indeed, we risk this optimization in an extreme case. So here we have to tell the compiler another thing, an additional thing, namely that this variable can be modified externally. Now, the classical way of doing that was the keyword volatile in C and C++. But the semantic around volatile is not very precisely defined. And it's not to be used for concurrency. There were two basic usages for volatile. Let me go into that direction a bit as well. One of them was in the context of interrupt handlers. And let's have in mind the settings. So until around the year 2000, multi-core CPUs were rare. So the standard was, even for performant computers, was to have a single CPU. So volatile was so that the compiler doesn't optimize something here because it depends on this being an external variable, but also the reordering was not such an issue at that time. Indeed, if we are in an interrupt context, then the compiler should refrain from using the result and should obey the order here, but it was not very precisely defined. The other thing that was also used was memory mapped input-output. Now, that's a completely different story. And if any of you have some experience with programming Arduino or microcontrollers in general, that's used a lot. You have something that from the programmer's point of view looks like a variable, but reading that variable or writing to that variable has an effect on the device. So I don't have a very clear example in mind, a very available example in mind. I cannot but point to the documentation for some microcontrollers and see there. So there are operations that are commanded by writing something to an address in memory, in something that looks like memory, but the writing itself has a semantic. And in that case, you want that the corresponding variable, so it's something that looks like a variable from the program point of view, when you write something to it, so each assignment corresponds to a single write, and each usage of the value corresponds to a single read. But it's not very precise, so it's not used as such a lot. Now, going back to here, what I need to tell the compiler and the CPU is the following. I want the assignment here to happen after all the code that I've written before has the effect written in memory. Here, I want to tell whatever is written after the read instruction must happen after I execute the read. And so I have those memory order specifications. So first of all, what I've been talking about for a few minutes is those acquire and release. Release is what I need. Where I need here. So release means, well, I've written something and now I release it to the public. So if I look here at memory order release, a store operation with this memory order, store means anything that writes to the variable. So that includes fetch, add, or whatever, because it writes something to the variable. no read or write in the current thread can be reordered after this store. So this means no operation that occurs in the same thread and it's written in the code before the atomic operation may be executed after the write atomic operation. So all writes in the current thread are visible to other threads that acquire the same atomic variable. And memory order acquire, a load operation with this memory order performs the acquire operation on memory location. No reads or writes in the current thread can be reordered before this load. So effectively, I should use release when setting something that, well, I did something and now I release it to the public, and acquire where I read something that I use as a flag, as a sign that something has been written. And if the value that I read is the expected value, then I can use something else that's written in memory. So here is release, here is acquire. Now this raises the question: what should be here at delete reference counter? So what memory order should I put here for fetch subtract?
Well, it's both read and write, so probably the one probably release, because that sounds more restrictive.
They are complement to each other. It's not that one is more restrictive than the other. It depends on what I'm going to do next. And what I'm going to do is, here I'm going to delete the object. So I do something that depends on the value here.
Oh,
so this should be an acquire.
Yeah.
Because I'm going to do something afterwards. Now, it may be acquire release. Let's see. Or maybe incrementing the reference should be with something. Anyway, it's a bit hard to analyze those things. You have acquire release, which is both acquire and release. You have relaxed, which is only for, it doesn't have anything to do with other, it doesn't have constraints about other variables, but the atomicity of the operation is guaranteed. So if I have an increment or an add something, it's performed correctly. But it can be reordered at will. The strongest one is sequential consistency. Sequential consistency has to do with the fact that even if we have a single CPU, at a micro level, I can see a distributed system here. So each CPU core is a node in a distributed system at a very small scale. And so the order of events may appear differently for different CPUs. And with sequential consistency, I say, no, I want to impose a sequential order on all the operations. So all the operations that are with the flag sequential consistent must be seen in the same order on all the CPU cores. Otherwise, nobody prevents the CPU for showing two atomic operations happening in different order on different CPUs. How to give an example of that? especially if I have multiple atomic variables. Imagine that on one thread, I have two atomic variables, A and B, and on one thread, I both have a value of 0 initially. On one thread, I increment A. On another thread, I increment B. Now, in the beginning, I have the values 0, 0. In the end, I have the values 1, 1. But in the meanwhile, I can have a pair of values of 0, 1 or 1, 0. And if I don't have sequential consistency, it's not disallowed that one thread sees variable A to be 0 and variable B to be 1, and another thread sees variable A to be 1 and variable B to be 0. It's not forbidden that such a messy thing happens, unless I put sequential consistency allowed. And all that, if one thread sees, let's say, A equals 1 and B equals 0, then no thread is allowed to see A equals 0 and B equals 1. Again, with sequential consistency. So, bottom line with atomic variables, well, not bottom line, I have another 10 minutes and I will add a new thing about the atomic variables. But almost bottom line is that for simple operations, that they are very easy to use and they are fast. However, composing the simple operations into more complex ones is a big can of worms, and it's quite hard to achieve correctly. However, the most powerful operation that we have on atomic variables, and that's also used for implementing mutexes and so. Where is it? Is this one, compare and exchange. We have load and store, which are assignments to and from, and are put as such so that I can specify as well the memory requirements. So store, I put the value and the memory order, and same for load. And now I have compare and exchange. Compare and exchange means I have two arguments, the value to be written to the variable and the expected value of the variable. And the semantic is the following. If the current value is equal to the expected one, then the current value is replaced by the parameter here, and the function returns true. Otherwise, so if the current value is different from the expected one, then this doesn't do anything and returns false. And this is very powerful because it allows me to do some more complex operations. For instance, instead of doing here a fetch add, I can do the following thing. I can say I'm doing the following. Doing 64. Temporary variable equals some load. Relaxed, I don't care much about the memory order, uint64t. And now, since I'm only incrementing the value, I will say temporary plus equals 1. But what's important, I can do whatever I want with this. I can do a more complex operation. And now I say sum compare exchange, I'll come to the difference between strong and weak. Actually, I need to do something else, and let me do it this way. Old value equals load. I create here a new value equals old value plus 1, but it can be any function of the old value. And now I expect it to have the old value. And if so, I set the new value. Now, it may succeed, in which case I'm done, or it may fail, in which case I have to do it again. So I will have this in a loop. And I'll put it as a do while. Doesn't work like this. Okay, then I will do a while true. I do this. And if the compare and exchange succeeds, then break. And here I end the while loop. So back again, I read the value, I compute the new value. And if the variable hasn't changed in the meanwhile, I write the new value. And this is an atomic operation, so it covers for what happens here. Now let's run it. It takes quite a bit longer, some 4 times longer than previously, but I have the correct value. And the good news is that I can put here any function as complex as it needs to be. So I'm not limited to simply adding a value. For instance, I can do something like if it's I'll put it like this, and I say if old value let me see, equals 8 million, then new value equals 7 million, well, 8 million minus 1. Else, if old value is even, I say new value equals old value plus 1, and else new value equals old value, sorry, plus 2, and here is minus 2. So I count even numbers up to 8 million. When I reach 8 million, I decrease by 1, and then by 2. There's something wrong with the compiler here. Rebuild solution. I guess I should put here 8 million and 1. to have it better. Oh, anyway, so bottom line is that I can do a more complex operation. Get the same value each time, but I have to understand exactly what's the issue here. Should I put something like this? No. Anyway.
I think it's because you have to increment 4 million times to reach 8 million, and then you decrement 12 million times.
Oh, yes. Yes, of course. 16 and let's say 16 and 1. Okay. That's good.
Yeah.
And I guess it should have been old value minus 1, but anyway, you get the idea. So I can put something more complex. And now what about compare and exchange strong versus compare and exchange weak? Compare and exchange weak is allowed to fail, so to not do anything and return false even if the current value is equal to the old value with a very small probability. Typically, this is allowed, and well, it's not a big deal if very rarely this fails spuriously. On the average, it is more performant than the compare and exchange strong. Now, the other things are, first of all, what I'm doing is that I'm repeating here. So it's, in some cases, I can waste a lot of CPU time, but by having all the threads repeatedly doing some computation that gets discarded because someone else did it before. So the performance issues are to be considered. The good thing, and those are so-called lock-free algorithms, the good thing is that if a thread, since we don't have mutexes, if a thread blocks for whatever reason and doesn't continue execution, it doesn't prevent other threads from running. So that's the good news, and that's one of the reasons those algorithms are used. And I'll end up with a warning. So everything that I'm doing here, I stand on the assumption that if the value, the current value of the variable is the one that I loaded here, is equal to the one that I loaded here, it means that nothing relevant has been happened in the meanwhile. Now, sometimes this assumption is correct, like here. Sometimes it's possible that some other threads did some operations that by chance set the same value here, but the context is different, so that the computation here is invalidated. And the latter is called the ABA problem. And you have here some detail on that. Okay, so we stop here. And well, I remind you to ask questions, to interrupt me if you have any, and thank you for doing so. If you have any questions now, please ask.